Okay, 14.5 and 6 deal with conservation of energy, and this is a good time to introduce some terms here. So the first thing we're going to talk about is a conservative force. And this is a force where the work is independent of the path. So forces that typically fall under this category are forces like the weight. Doesn't matter what path you take as you raise an object up in the air. The work that is done is dependent on the height you raise it. Another conservative force we use is elastic spring. With the elastic spring, so those are conservative forces. Let's juxtapose those with a non-conservative. And these are forces that usually end up creating heat or dissipating heat in our system. So one of the main ones is that we deal with is friction. And friction is non-conservative because the longer the path, the more friction you end up, greater the work due to friction. So let's talk a little bit also more about energy. Now we've been using kinetic energy, and one form is 1/2 the mass times the velocity squared. Now we're going to add to this potential energy. And we can have typically two forms of this. We have the gravitational potential energy, or the potential energy associated with the height of an object, which is the mass times acceleration due to gravity times its height. So the potential energy is like stored energy. And then we also have the 1/2 kx squared for a spring. Now this potential energy for a spring is typically positive, because when you squish the spring, it ends up applying a force, and you move in the direction that the spring pushes you. Or if you overextend the spring and the spring pulls you back, you end up moving in the direction that the spring is pulling you back. So with these ideas, we can develop the concept of conservation of energy. And we're really going to use the energy work equation to do this. So we have this T1, and then we added to it the summation of work from 1 to 2, and that was equal to T2 as before. But now we're going to pull out the potential energy from this work, and the potential energy that occurs initially in our problems. We'll think of this as sitting on the left side. So V is our potential energy. So potential energy. So we have an initial potential energy. Maybe you have something up on a hill that is high and it's about to slide down the hill. then it would have energy to start with. Whereas we can end up with potential energy. Say we have a lot of kinetic energy here and we drive up a hill, we end up stopping at the top of the hill. Now we have potential energy associated with that. And there are still some work terms left over that we haven't pulled out here. And these are our non-conservative energies, like the work associated with friction, for example, in here. So you can think of these conservative, non-conservative energies as sucking away some of the energy from our system that could be used to move it or to position it to, say, a higher elevation. So now if we have systems that don't have any non-conservative energy in them, then this relationship reduces down to T1 plus V1 equals T2 plus V2. This is our relationship for the conservation of energy. Okay. And if we have a system with many different kinetic energies and potential energies to start with, we can get a system summing all the kinetic energies and potential energies in the output. So let's look at this example. Complicated examples can sometimes easily be solved using conservation energy methods. So here we have a collar that is sliding down a rod and to its new position from A to C. And here are the dimensions associated with it. Notice this spring, which is initially 0.75, is extended to 1.25 meters. So our delta in the spring, our change in length, is going to end up being 0.5 meters, which is just essentially 1.25 minus 0.75, the original length of the spring. So that's the unstretched length. We are missing a K, so let's put that in. K equals 3 newtons per meter. So now let's figure out our conservation of, I don't know why I'm going to C instead of B, but it is what it is. Okay, so our initial kinetic energy is, we have an initial velocity, so we're looking at 1/2 2 squared times our mass, 2 kilograms, plus our height. So I'm taking, pretty much you have to decide where, and for me I'm going to take the datum line as this bottom position here, so we start out at a higher, so we start out with some potential energy, so it's going to be 2 times 9.81, and we are a meter up in the air, so that's our potential energy initially, and then we will end up with some kinetic energy. Looking at 1/2, our mass is 2 times the velocity at c squared. We don't know what that is, but we're also going to we'll have some energy stored in this spring when we finish up. So let's add that to this 1/2 k of 3 times x squared, so 0.5. So we inspect our equation, we see that we have one unknown. We can solve for our velocity directly at c. So our velocity at c, after solving this relationship, can ends up being 4.82 meters per second down. Now you can see how much quicker that is than going through a more detailed conventional kinematics approach. Okay, so let's do another example. This is 1473. So we've got a roller coaster here with two loop-de-loops, and we want to figure out what the height of this hill is so that this car has enough energy to go around both loops. So let's just let's start out with the energy equation. So TA plus VA equals, let's do potentially the first loop first. Just go TB plus VB. Now, since our kinetic energy initially is 0, because we have no velocity to start with, it's there, and then we have a 700 kilogram car that is up a height h times 9.81 meters per second squared for our potential energy to get this whole thing rolling. Then at B, so h is unknown, at B we have 1/2 our mass, which was 700 kilograms, times our velocity squared at B, but we also are going to have some potential energy left over, and that is going to be mass of 700 times our height of 15 meters, and G is 9.81 meters per second squared. Okay, so we see we have two unknowns here and here, so we have to deal with those. In order to get this h, we need to figure out what velocity of B is, and I think we can use some kinematics to do that, or rather some kinetics. Let's look at the equation of motion. Okay, so for a free body diagram here, looking at B, we have a normal force of the track on this car, and then we have a weight, and this is going to be equal to our normal acceleration times our mass. Okay, let's sum our forces in the normal direction. We've got n plus the mass times acceleration for our weight, and then this equals our mass times our normal acceleration of velocity v squared over rho. For rho, we're going to have to take this as half of that height, or 7.5. Now, when we hit the top there, the minimum, with the minimum speed, n is 0 in the minimal case, and we'll just make it around if that's the case. So, and this gives us our velocity squared for B. Now, we could calculate this for C, and we would find that we would get a smaller velocity, but that's intuitively, we know, since there are no losses occurring here, that if we can make it through B, we should be able to make it through C, because when we get to B, we are actually storing some potential energy back again, and it's enough with the kinetic energy to get us around C then, because it's a lower position. So now we can just directly plug this VB into here and solve for H, and H turns out to be 18.75 meters.